Okay, so right now we're going to talk about magnetic fields. Magnetic fields are basically produced by electric currents, which can be microscopic currents in wires or microscopic currents associated with electrons in atomic orbits. This is most familiar with the Earth's actual magnetic field that it exhibits, as well as the magnetic field that you see here from two magnets underneath. As you can see, the iron shavings are attracted to it, and they form certain lines that protrude from the north and the south poles. Go on. The magnetic field is defined in terms of force on moving charge, which is called the Lorentz force law. The Lorentz force law is the measure of an electric force with the relationship with a magnetic force. And the basic unit for a magnetic field is the Tesla, which can be seen from the magnetic part of the Lorentz force law. And this is measured in newtons times seconds divided by coulombs times meters. The magnetic quantity B, which is being called the magnetic field. See with the bar magnet, the lines of the magnetic field from the bar are from closed lines, as you can see, going around here and going around here. And as it gets closer, they start to form around here. As you can see, these two poles interact with each other, and they form sort of a stronger bond between these iron shavings here. And so it's normally taken to be outward from the North Pole and then into the South Pole of the magnet. As you can see here, when you put different magnets along with iron shavings and then adding some compasses, you can tell where the lines actually go because of the compass's pointed direction. As you see here with this smaller compass right here, that is in line with the actual closed line that is going on at about this point, and it's going to be doing a little revolution around here. And the same one for right here. There's not as much shavings here, but as you can see, if we add more iron shavings right here, you get an effect that should reflect what's going on with the other ones. As you can see here, the iron shavings are pointing towards the north side of this pole, as is this one. And then as you move on to this magnet, to this compass here, you see some more shavings which obviously point towards the North Pole, and the compass arrow pointing towards that direction. And as you move to this one is in the middle of the actual magnet, and you have the north side pointing upwards, which is reflective of the fact that once you reach this point right here and then traverse along the poles, it's going to be an arc going around here, and if you hit it right in the middle, it's going to be in the middle of this arc, which would reflect pointing straight upwards, and then this arrow pointing straight southwards. So you may be asking how this is relevant in real life other than just bar magnets. As you can see here, the Earth, much like a bar magnet, is surrounded by electric currents. So you would observe these magnetic lines around here that represent the current that is traversing from the north to the south pole. And if you go down a little here, you see that the Earth, much like a bar magnet, has very similar electric current lines. So you have the north traveling all the way to the south, and then inversely here you have the south, and then those magnetic fields showing that it traverses from there to the north side of the bar magnet. This picture here explains what the actual current and the relationship between the current and the actual field. So as you see right here, this right hand has this electric current going through this wire here, and as you can see, there's these little circles or orbits around this, which demonstrates that the current is influencing the matter around here, basically the magnetic field, and it's traversing from north and south and vice versa.